video, we will study the interrupts of 8085. So let's start with our topic. We have So what is an interrupt? When the microprocessor it is performing certain tasks, that means it is executing a program instructions, and if any disturbance is given to it or any interruption is caused, like some peripheral device it is connected to the 8085 and it wants to communicate with the microprocessor, so that is called an interrupt. If we want to have an example of the interrupts in our day-to-day life, suppose a person is studying and meanwhile our mother comes have a tea in between. So while doing the work, that person is interrupted because the mother has come with the tea. So that interruption has stopped the programming, and when it has have a tea, finishes a tea, then again he started studying. So for some time the working of the processor it is stopped due to the interrupts. So these interrupts, they are just like the disturbance for a short time, and some work is done. When that work is complete, again the programming or again the functioning is resumed for the processor. So the interrupt is the mechanism So interrupt is the mechanism by which the processor is made to transfer the control from its current program execution to another program having higher priority. Suppose there are two programs written in the processor, and first the processor is executing the first program. Now in between we have the user, he wants that instead of executing this first program, the processor should first execute second program, and after it again resume the first program. So this second program is having higher priority. So what the interrupt is doing, it is changing the it transfers the control from its current program execution. Currently it is executing the first program, so it is transferring the control to another program which is having the highest priority. Then the second program will be executed completely, and again the first program is resumed and its further instructions will be executed. So this type of mechanism is called the interrupt. Now this interrupt signal, it is given to the processor by any of the external peripheral device. Peripheral device means the input-output devices which are connected to the processor, or those devices which want to communicate with the processor. So those devices, they are collectively known as the peripheral devices. So any of the peripheral device, they can give interrupt signal to the processor. They can interrupt the processor during its functioning and can stop its programming, that first execute this program and then do your work, whatever you are doing. So this interrupt signal, it is provided by the peripheral devices which are connected to the processor. Now this interrupts, they are what they are transferring the control to another program. So that another program is called a routine, a subroutine it is called, because subroutine, it is a type of sub program which is written at somewhere some other memory location. So the program or the routine that is executed upon interrupt, it is called the interrupt service routine. So that program which is written at different memory location, and that interruption it is called, so that interruption is called the interrupt service routine. So that program will be first executed and then the main program will be executed. After this interrupt service routine is executed by the processor again returns to the main program, and further instructions which are remaining, which are not executed, they will be then executed by the processor. So after execution of ISR, the processor must return to the interrupt program. So this was our main program. The processor was executing this main program. Suddenly an interrupt has been given to the processor. Suppose at third instruction, the third instruction of the main program, an interrupt has been given. So when this interrupt is given, the processor, it will execute the interrupt service routine, the subroutine which is written at different memory location. When that subroutine has been completely executed, it will return to the fourth instruction and then execute till the last instruction. So after execution of ISR, the processor must return to the interrupt program. Now let's see the key features which are involved in this interrupt mechanism. The first is so the processor, it should know that how much numbers like 2, 4, how many number of interrupts are given to the processor, and the type of interrupt signal, what are the types of interrupt signals which are given to the processor. So first thing we should know is the number and types of interrupt signals available to the 8085 processor. Next is the address of the memory where the ISR interrupt service routine is located for a particular interrupt signal. For every interrupt signal, there will be a ISR interrupt service routine, and that ISR should be executed. So we should know the address of the memory location where that ISR has been stored in the memory. Okay. And this address is called interrupt vector address, that is IVA. So every ISR, the service routine, it will have an address, and that address is called interrupt vector address. So we should know that address, that where the subroutine has been written, and that service routine we have to execute. The processor should also know about the masking and unmasking feature of interrupt signals. There are some interrupts, there are many types of interrupts available for the 8085. Now, out of those interrupts, some of the interrupts are maskable and some of the interrupts are non-maskable. Maskable means there are conditions when the processor can execute the main program, and after completing the execution of main program, then the processor is going to execute the service routine. And there are some interrupt signals which need to be executed at the same time when they are given. So the processor should know about the masking and unmasking, which of the interrupts can be masked, which cannot be masked. So this feature should be known to the processor. Also, the processor should know about the priority among the interrupts. Like if 4 interrupts are simultaneously given to the processor, now which of the interrupts should be executed first? So there are priorities defined for each of the interrupts, and according to that priority, the interrupts they are executed. Timing of the interrupt signals, at what time which interrupt has been given to the processor, and the handling and storing of information. So the processor should know these are the key features of the interrupt signal in the of any of the microprocessor. These key features should be kept in mind whenever we are dealing with the interrupts. First is number and types of the interrupt signals available, how many interrupts and what are their types. Then address of the memory where the interrupt service routine has been written, that is we should know the interrupt vector address. Then masking and unmasking features should also be known, that which of the interrupt can be masked and which cannot be. Priority should also be known, timing and handling and storing of the information about the interrupt program. Now let's study the types of interrupts in 8085. How the various interrupts they are classified in the 8085. The interrupts in the 8085 they are classified on 3 bases. First classification is hardware and software interrupts. Second classification is maskable and non-maskable interrupts. Third classification is vectored and non-vectored interrupts. So in these 3 ways, the interrupts in 8085 they can be classified. First, we will study about the hardware and the software interrupts. Hardware interrupts means those interrupts which are given by some signals or some external circuitry is there for those interrupts. So through any signal or through any external circuit we are interrupting the processor. So those interrupts come under the category of hardware interrupts. Software interrupts are like instructions are written in the main program, and that instruction is providing the interrupt to the processor. So under the category of hardware interrupts, there we have trap, RST 7.5, RST 6.5, These are some of the interrupts in 8085 which come under the category of hardware interrupts. These interrupts are provided to the 8085 through some external circuit or some signal is there, like INTR. Its full form is interrupt request. This is a signal. A pin is, because 8085 it is a 40 pin IC, so there is a pin for this INTR, and when this pin is high, it means this interrupt is being given to the 8085. Other, like for trap RST 7.5, 6.5, also we have a circuitry, and through that circuitry the interrupt is provided to the 8085. So due to some circuitries involved in this, that comes under the category of hardware interrupts. Now software interrupts, these are the instructions which are written directly in the program, and we have here RST 0, RST 1, so starting from RST 0 to RST 7, we have the software interrupts. So software interrupts are from RST 0 to RST 7. These instructions, RST is for the restart. So these restart instructions, they are directly written in the main program, and the interrupts, they are provided directly through these instructions in the processor. So this is the first classification, hardware and the software interrupts. Second classification was maskable and non-maskable. There are some interrupts, like there are priorities defined in the 8085 interrupts, because several interrupts are available. So if simultaneously 4-5 interrupts are given to the processor, so how the processor is going to decide that which interrupt is to be executed first and which as second position, which is having the last priority. So maskable interrupts are those interrupts which can be masked for some time. The processor can make the interrupt to wait for some time. First it is going to complete the execution of the main program, and after that it is going to execute the service routine for that interrupt. So those interrupts that can be masked for some time, they come under the category of maskable interrupts. And those interrupts which cannot be masked, like which are having the highest priority, the processor has to stop its execution whenever these type of interrupts are being given to it. First it has to acknowledge that service routine, that service routine has to be executed, and after that the processor can resume its programming. So those interrupts, they come under the category of non-maskable interrupts. So maskable interrupts can be blocked for sometimes. Non-maskable, they cannot be blocked. They are having the highest priority. Now masking of the interrupts, it can be either through software or through hardware. So there can be any of the method, software or hardware method for masking of interrupts. Now, among the 8085 interrupts which are available, maskable interrupts are all the interrupts like RST 0 to RST 7 and RST 7.5, 6.5, 5.5. These all are maskable interrupts. There is only one interrupt which is non-maskable and which is having the highest priority. It is trap. So the next classification of interrupts is vectored and non-vectored interrupts. We know that in the interrupts, every interrupt will have an interrupt service routine, and that interrupt service routine, it is written at certain memory location in the memory of the microprocessor. So the microprocessor should know the address of that memory location where the interrupt service routine is written. So the vectored interrupts, they are those interrupts which are having fixed address for that memory location. Means the address of the interrupt service routine, it is fixed for that interrupt. So those types of interrupts are called vectored interrupts. Now non-vectored interrupts are those interrupts for which the interrupt vector address, that is the address for the interrupt service routine, it is provided by the external device which is interrupting the microprocessor. So we can say that vectored interrupts, they have fixed interrupt vector address, and non-vectored interrupts, they require the interrupt vector address to be provided by the external device. So this was the third type of classification of the interrupts. We studied the three classifications, that how in three ways the interrupts can be classified. First was software and hardware interrupts, second was maskable and non-maskable interrupts, and third was vectored and non-vectored interrupts. Now in 8085, the various types of interrupts which are available, which are given to 8085, let's study those interrupts, and which interrupts are vectored, maskable, software, how they are classified in these various categories. So interrupts in 8085. So we have INTR, which is the interrupt request. Its full form is interrupt request, which is sent by any of the external device which want to interrupt the 8085 microprocessor, and in response to it, the 8085, it produces the signal INTA, that is interrupt acknowledge. Okay, so this is the first interrupt in 8085. Then we have trap, then RST 7.5, 6.5, 5.5. These are three different interrupts, and then we have RST0 to RST7. This RST is for the restart. Its full form is restart. So it's RST 7.5, 6.5, 5.5. So these are the various interrupts present in 8085. Now out of these interrupts, some of the interrupts are software or hardware interrupts, some of them are vectored, non-vectored, and some of them are maskable or non-maskable. So let's see what are these. First is INTR. I have said that INTR is the interrupt request which is given by any of the external device which want to interrupt the 8085. Now INTR, it is a hardware interrupt. Okay, that means it is a signal. It is in the form of a signal which is given by the external device. Means there is a circuitry which is interconnected with it. There is a circuit for it to be given by to the 8085. That is why it's an hardware interrupt. There may be any other switch which would be pressed and then this interrupt will be given to 8085, or there may be some circuit which is connected to it, or there may be a pin of 8085 which is giving this signal to 8085. So there is a hardware related to this interrupt. That is why it's an hardware interrupt. Also, this is a vectored interrupt. Okay. Now, this vectored interrupt means that it is having a fixed interrupt vector address for it, but this address, it is provided by the external device. Or this address is decided by the hardware which is connected to it. Now, whatever pin, at what pin the signal is being given to 8085, so that address is decided by the hardware circuitry. And also this is a maskable interrupt. So we can say that INTR, if it is asked that whether it is a software or hardware or maskable, non-maskable, which type of interrupt it is. So it is a hardware, vectored and maskable interrupt. Next interrupt is trap. This interrupt is very important because it is having the highest priority among all the interrupts. So it is a highest priority interrupt. Also, this is a hardware, vectored and non-maskable interrupt. Hardware because some circuit is related to it. Okay, so this will be a hardware interrupt. Vectored, it is having a fixed interrupt vector address. Okay, we will study its address when we will study it further, that what are the address related with each of the interrupts. And this is a non-maskable interrupt. Whenever this interrupt is given to 8085, the microprocessor has to acknowledge it. It has to stop whatever function it is at currently that time it was performing. It would stop that function and will first acknowledge the trap interrupt. Then we have RST 7.5, 6.5 and 5.5. These three interrupts, they are also hardware, vectored, but maskable interrupts. Trap was hardware, vectored, non-maskable, but these three are hardware, vectored and maskable interrupts. The next interrupts in 8085 are RST0 to RST7. Means we have RST0, RST1, 2, 3 till RST7. Now these interrupts, they are software, vectored and maskable interrupts. Okay, up till now we have studied that trap, INTR, all these were hardware interrupts, but RST0 to RST7, they are software. Vectored interrupts, vector means they have fixed addresses which are already defined, and maskable, that they can be masked using the RIM and the SIM instruction provided in the 8085 instruction set. We will study the RIM and SIM instructions later on. So we have known here that we have got to know that what are the interrupts which are available in 8085, trap, INTR, RST0 to RST7 and RST7.5, 6.5, 5.5. These are the interrupts which are available in 8085. Now whenever these interrupts, they are given to the 8085, how this microprocessor, it is going to handle the interrupts, what procedure it will follow. So let's study the interrupt handling procedure, how the 8085 handle all the interrupts when an interrupt signal is given to it. So when an interrupt is given to the microprocessor first step is to save the So the first step is to save the program counter contents and information about the current state of the flags and the registers in the stack. So we know that interrupt when the microprocessor it is performing a program, it is executing a program. So when it is first executing, suppose this instruction, suppose INRC is written here and this is written JNZ. Okay, something is written here in the program, there are instructions. So when the microprocessor it is executing this instruction, it will save the, because first step is to fetch the opcode for this, then decode that instruction and then execute that instruction. So when this procedure is being followed by the microprocessor, the address of the next instruction it is stored in the program counter. The address of this instruction, wherever it is written in the memory of microprocessor, it is stored in the program counter, so that when its execution of INRC, this instruction is being done by microprocessor, after that execution it will know that the second instruction which it has to execute, it is written at this memory location. Like this is stored at 2080 and this is stored at 2081. So the address of next memory location will be stored in the program counter. So through this program counter, microprocessor is knowing that the next instruction which it has to execute, it is written at this memory location. So when interrupt is being given to 8085, it was executing some program. Some program is being executed by 8085, or some function or operation is being performed by the, at the time the microprocessor was performing that function. So the address of next instruction, it has been already stored by program in the program counter. So suppose at this JNZ or at INRC, the interrupt signal is given to 8085. So when interrupt is given, microprocessor has to stop further execution of the instruction and it has to jump at that memory location where the interrupt service routine is written. Suppose it is written at 8050 till it is written up till 8060. So between these 10 locations the interrupt service routine is written. So when a microprocessor will jump to this location 8050, it will run the interrupt service routine. And how it is going to know that the program where it was interrupted, the next instruction it has to execute, it is stored in this program counter. So the save the program counter contents the address of the next instruction and information about the current state of whatever what is the condition of the flag register. There we have sign, zero, parity, carry flag, auxiliary carry. Suppose any arithmetic and logical operation was already performed in the program, and suppose zero flag it is being set, carry flag is zero and sign flag is zero. So the conditions of the flag also the microprocessor has to store somewhere, so that it should know that these were the flags status, and I have to resume my work again. So for resuming the working or the operation of the microprocessor, the address of the next instruction which is in the program counter, the status of the flags and the registers, like whatever the condition of accumulator B, C, D, E, these HL, whatever the contents of these registers, all these are stored in the stack. And stack is what? It is a group of memory location which is storing the temporary data for microprocessor. So this temporary memory storage, it is used to store the contents of the program counter, the status of the flags and the contents of the registers of 8085. So after executing the interrupt service routine, the microprocessor can resume its operation, its execution of the program by getting all the conditions, all the status of the registers and flags and the program counter. So first step is to save all these things so that microprocessor can further resume its working. Now second step is to load the program counter with the beginning address of an interrupt service routine and start to execute it. So at this step, INRC, the microprocessor is interrupted and the address of the next instruction, it is stored in program counter, and this address is already stored in the stack. So now what microprocessor has to do? It has to jump to this memory location 8050. So this address of the interrupt service routine, wherever this interrupt service routine is written, it comes in the program counter. So now the contents of program counter in the second step, they will become 8050. So the microprocessor, it will now start executing this interrupt service routine. Earlier address, it is already being stored in stack. It is not being lost by the microprocessor. It is being already kept safe in the stack, and next address where ISR is written, it is stored in the program counter, and the microprocessor, it will start executing this ISR. So second step is to load the program counter with the beginning address of an ISR and start to execute it. Next step is to finish the ISR. So where the in the second step, the microprocessor has started executing the interrupt service routine. Now where it has to stop that execution? The execution will stop when the microprocessor will encounter this instruction. When it is executing this return instruction, it means the ISR has been finished and it has to return to its main program where it was interrupted. So when this the third step is to finish the ISR execution when the return instruction is executed. Fourth step is to return to the point in the interrupted program where execution was interrupted. So the microprocessor, where we taken the example that it was interrupted at INRC instruction. So the microprocessor will return to that instruction where in the interrupted program where execution was interrupted and will start the further execution. It will get the address from the stack because in the stack we have stored the address of the next instruction was stored in the stack. So that address will be regained by the microprocessor, and all the conditions of the flags and the register will also be regained by the microprocessor, and it will start the further execution of the program which was interrupted. So in this way the microprocessor handles the interrupts in when they are given to it. Okay, these are the steps which the microprocessor follows. Now, we have studied the 8085 interrupts, that we have INTR and all those interrupts, RST0 to RST7, trap, all we studied. Now, let's see the sources of those interrupts and their vector addresses. What are the vector addresses which are associated with these interrupts? So out of the interrupts which are available in 8085, we have RST0 to RST7. These were the software interrupts. So first we will study the vector addresses for these software interrupts. RST0. So these were the software interrupts. Now for RST0, we have the vector address 000H. Now the addresses in the microprocessor 8085, they are of 16 bits. So these 16 bits in hexadecimal notation, they are denoted as the 4 bits 0000. So 0 for 0 we have this, for this 0 we have the 4 bits, for this we have 4 bits, and for this also we have 4 bits. So these total are 16 bits memory addresses in 8085. Now these 16 bits, they are in hexadecimal notation. They are denoted like 000 and 0. Now for RST1 we have 0008H. For this we have for 3. So you can see that the vector addresses, they are also having a pattern. We have 00, then 08, then 10, 18, 20, 28, 30. Last is the one which is having 32. So these are the vector addresses which are related to the software interrupts RST0 to RST7. Okay, these were the restart instructions. Because they are software interrupts, so it means that they can be written in the program as an instruction. So these are a part of the restart instructions. We have 8 interrupts in this category. Also these are 1 byte instruction. They, when they are stored in the microprocessor memory, the user, it writes only these mnemonics for this, and when these instructions, they are stored in the memory of microprocessor, they are stored in the form of machine code. So every instruction will have a respective machine code which requires only 1 byte in the memory. So these are 1 byte instructions, and the subroutines, the ISR for these interrupts, they are written at these memory location. So their ISR address is fixed. That is why these are the vectored interrupts. Okay. Now next we were having trap and INTR. So their vector addresses are now out of these interrupts, trap is having the highest priority. And INTR is having the lowest priority. Now for INTR, the address is decided by the hardware. For trap, we have 0024H. RST 7.5, we have 3CH. 6.5, we have. For trap, it's 24. It's for 3C, then 34, and then 2CH. These are the vector addresses where the service routine for these interrupts is being written. Now INTR, it was maskable. Trap was non-maskable. And all these are also maskable interrupts. Then there is level also associated with these interrupts. The levels are INTR, it is a level triggered interrupt. Triggering, we will study later on that how they are triggered according to the clock pulse. The clock pulse, when its level will come, then this interrupt will be on. Okay, so this is level triggered. Trap is also level triggered. Then RST 7.5, it is rising edge triggered. Edge triggered interrupt, it is 6.5 and 7.5 are both level triggered. Priority, we have already written that trap is having the highest priority and INTR is having a lowest priority. Among 7.5, 6.5 and 5.5, 7.5 is having highest priority. That means trap is the first, 7.5 is second, then 6.5 third, 5.5 fourth, and INTR having lowest priority. Okay, and after that the RST 0 to 7, they are executed by the 8085. So these were the vector addresses related to the 8085 interrupts. Now how these interrupts are masked in 8085, how the masking procedure is done. We studied that INTR and RST 7.5, 6.5, 5.5, they can be masked by the microprocessor. Okay, so we have masking can be done for the 4 interrupts. Okay, so for these 4 interrupts the masking can be done. So let's see the circuit for it. Trap is a non-maskable interrupt, so it will be directly given and it's in vector addresses 0024H. Okay, now masking has to be done for the 4 interrupts. So let's draw the circuit on a new page. So this is the circuit diagram for the masking of the interrupts, and in this you can see that we have the four interrupts: RST 7.5, 6.5, 5.5 and INTR, which can be masked. And to RST 7.5 we have the D flip-flop, and then here we have the SR flip-flop, which is the interrupt enable flip-flop. Now to every this interrupts we have a masking bit here. So let's see the explanation for it. By default, these interrupts, they can be masked by this reset signal if the interrupt is given to the microprocessor, and we want that this interrupt should not be executed by microprocessor. So we can give it a reset signal. We can press the reset button, and we can reset the system. The whole system will be reset, will come to its initial conditions, and then that interrupt will not be executed, it will be masked. So by default, this reset signal, it can be used to mask the interrupts. Now, so the maskable interrupts, they can be by default masked by the reset signal, and no interrupt is recognized by the hardware. Next, we have the interrupts. They can be again enabled by the EI instruction, enable interrupt. We have four instructions related with the interrupts. The first two are the disable interrupt and enable interrupts. These two instructions, they are used to enable or disable the interrupt enable flip-flop. You can see here we have the interrupt enable flip-flop. So to disable and enable this flip-flop, to stop or to reset or reset it, we have these two instructions. So this instruction EI is used to enable the interrupts. The three RST interrupts, RST 7.5, 6.5 and 5.5, they can be selectively masked by loading the appropriate word in the accumulator and executing the sim instruction. In the sim instruction, we have the bits specified for the masking of these three RST interrupts. We will study the sim instruction later on, and by loading that appropriate word, the appropriate data into that sim instruction in the accumulator, we can mask these three interrupts: 7.5, 6.5 and 5.5. So this was the third step. Now fourth we have all the maskable interrupts. The maskable interrupts were INTR 7.5, 6.5, 5.5. So these interrupts, they can be they are disabled whenever an interrupt is recognized. Whenever any of the interrupt except these maskable interrupt is being given to 8085, then these interrupts, they are disabled, and that interrupt which is given first, that interrupt will be executed. And also they can be disabled by using the disabled interrupt instruction. So this is all that how we can have the masking of the interrupts. They can be masked by default, they can be masked by the reset signal. Then the interrupts, they are enabled after masking. If we want to resume those interrupts, then we can enable them by the EI instruction. And the three RST interrupts, they can be selectively masked using the SIM instruction, and they can be disabled by executing the DI instructions. So we have EI, DI and SIM and RIM instructions for it. Now in the circuitry for the masking of the interrupt, you can see that this RST 7.5, this is a edge triggered interrupt. So for and all the rest, they are level triggered. So for this edge triggered, we have the D flip-flop here to recognize this edge of the clock pulse. Then we have the masking bits for these three interrupts, and these masking bits, they are provided by the SIM instruction. So if this bit is 1, then it is made 0. We have a bubble here. So this is made 0, and 0 will give us that output through this. Now we have INTR, and here we have the OR for it. Then we have the interrupt enable flip-flop. This signal is given to this flip-flop. So when this request is given, then INTR signal will be enabled. This interrupt will be enabled, and the address for this will be given from the hardware. Here this hardware will provide it the address of this INTR interrupt. So this is how they are masked. So in this masking, we studied that the SIM instruction is used to mask the the three RST interrupts. So let's study the SIM instruction, and then we will study the RIM instruction. SIM instruction. The full form for this SIM instruction is set interrupt mask. S for set, I for interrupt, and M for mask. So its full form is set interrupt mask. Now this instruction is used to mask or unmask the RST interrupt. So this instruction is used to mask or unmask the RST hardware interrupts. We have RST software interrupts also, RST 0 to 7. They cannot be masked by this SIM instruction. Only the RST hardware interrupts, that is 7.5, 6.5 and 5.5, they can only be masked or unmasked using this instruction. Now when this instruction is executed, so when this instruction is executed, the SIM instruction, it is going to read the contents of the accumulator, and accordingly it is going to mask or unmask the interrupt. This instruction is written in the program of the microprocessor, and this instruction is going to read the contents of the accumulator. So we have to provide the control word. The control word is the contents of the accumulator, and that control word will affect this SIM instruction. Those 8 bits, they are specified. So every bit of the content of the accumulator, because accumulator, it is a 8-bit register, so those 8 bits, they are specified, they are fixed, and according to that content, the masking and unmasking of the interrupts will takes place. So let's see the format of the control word. We have 8 bits in the accumulator. So those 8 bits are like the 8 bits, its positions are D7, D6. Okay, D7 is the most significant bit and D0 is the least significant bit. Now D7 is these 8 bits, they are specified like this. D7 is SOD bit, D6 is SDE, D5 are the don't care bits. So don't care bits, they are represented by XX, means whether this bit is 0 or 1, it doesn't matters. Now D4 is RST 7.5, D3 is MSE, mask set enable, D2 is mask the 7.5, D1 is mask 6.5 and D0 is mask 5.5. Let us see the explanation for each of these bits. SOD bit, it is the serial data to be sent. This is serial output data. Full form is serial output data. Okay. So when the microprocessor 8085, it is performing the serial data communication, then it has some serial input and serial output, means some data is being input to the microprocessor and some is got out, so that would be the output data. So that output data, that output bit, it is provided by this D7 bit. If it is 0, then 0 will be given as an output bit. If it is 1, then 1 will be given as an output bit, because the microprocessor, it deals in zeros and 1, so whether it will be 0 or it will be 1, so that bit will be given as an output during the serial data communication. D6 bit, it is the SDE, so its full form is serial data enable. Means this bit is used to enable the serial data communication. If this bit is 1, then serial data is sent. Means if this bit is 1 and this D7 bit it is 1 or it is 0, then that will be sent as the serial output data. If it is 0, then this bit will not be sent. So D6 bit, it is used to decide that whether serial data communication has to take place or it does not has to take place. So SDE, it is deciding the serial data communication, it is enabling the flip-flop. Then D5, they are the don't care bits. Means their value doesn't matters whether it is 0 or 1. Then we have RST 7.5. This bit is to reset the RST 7.5 flip-flop. We have seen that for the RST 7 interrupt, we have the D flip-flop. So this bit is used to reset that flip-flop, that is to make it 0. Reset means to bring it to its initial conditions. Okay. Then we have MSE, this is mask set enable. Means that this bit is used to enable the masking of these 3 interrupts. Means if it is 1, then only masking will take place. If it is 0, then these 3 interrupts, they will not be masked. If it is 1, then only masking will be done. That is why it is named as mask set enable. Then this M 7.5, it is set to 1. This bit is made 1 to mask the RST 7.5. This bit is set to 1 to mask 6.5, and this bit is set to 1 to mask 5.5. Okay, means if we want to mask the interrupt 6.5, then this D3 bit has to be 1 and this D1 bit has to be 1. Other bits should be 0. So this type of data, when this D3 is 1, D1 is 1, then 6.5 will be masked. If this bit is 1, then 7.5 will be masked. But this MSE bit, this has to be 1 for the masking of any of these 3 interrupts. If it is 0 and it is 1, then no masking will be done. So you can see here that this instruction, sim instruction, it is used for the masking of the 3 RST interrupts. Okay, and these 8 bits are of the contents of the accumulator. The 8 bits which we are giving to the accumulator as an input, those 8 bits, they will decide that whether the masking will be done or not. The next instruction we have is rim instruction. The full form for this is read, interrupt, mask. Okay, so this is used to read the status of the interrupt mask bits. So rim is used to read the status of the interrupt mask bits, that which of the interrupts they are masked in the microprocessor. And when this instruction is executed, the contents of the accumulator it is loaded with the current status of the interrupt mask and the pending interrupts. Which of the interrupts, suppose multiple interrupts are given to 8085. Now when 4-5 interrupts are given, then a microprocessor will execute them according to their priority. Suppose first second the interrupt which is having the priority at the second number, it is being executed, and third and fourth interrupts, they are pending. So which of how many interrupts are pending, what are these interrupts, so this information, it is provided by this rim instruction. Okay, also it is used So it is also used to read the serial data on the SID pin. SID is serial input data pin, and the data on the SID pin, it is stored in the MSB, that is most significant bit of the accumulator. Let's see the format of this rim instruction. So these are the 8 bits of the accumulator. the accumulator will be loaded with all the status of the interrupts which are masked, which of them are pending, and those 8 bits of the accumulator, then we will read each of the bit and then we will decide that which of them are pending in these interrupts. So SID, it is the most significant bit of the accumulator. D7 will be the SID bit, that is serial input data. So when the microprocessor is performing the serial data communication, then the external device, it will give the serial input data to the microprocessor. So that data will be provided at the SID pin. If it is 0, then this bit will become 0. If that data is 1, then this bit will become 1. So this bit is going to be changed according to that serial data pin input, that whatever the bit is available on this SID pin, that bit will come here in the D7 bit of the accumulator. Next bit is D6. This is I7.5. So this bit is set to 1 This bit is set to 1 if RST 7.5 interrupt it is pending. Like the interrupt which is having priority greater than this 7.5, which is like trap is being given to 8085. So this interrupt will be pending. Suppose trap and RST 7.5, they are simultaneously given to the microprocessor. So microprocessor will first execute trap because it is having highest priority, and at that time RST 7.5 will be pending. So this bit will become 1, showing the microprocessor that RST 7.5 is pending. First execute the trap and then acknowledge this RST 7.5. Similarly 6.5, this D5 bit, it is set to 1 if 6.5 is pending. And this is set to 1 if 5.5 is pending. Then we have D3 bit as the IE bit, which is the interrupt enable bit. So if the interrupts, they are enabled, that is we have given the EI signal, EI instruction is given and all the interrupts are enabled, then this bit D3 bit will become 1. Then we have M7.5, 6.5, 5.5. So this bit is set to 1 if RST 7.5 is masked. In the same instruction, we were having this D2 bit for the masking of the RST 7.5. Now, if that interrupt is masked, then in this 7.5, in this RIM instruction also, this bit will become 1 if RST 7.5 is being currently masked by the microprocessor. This bit will be 1 if 6.5 is masked, and this bit will be 1 if 5.5 is masked. So you can see that this RIM instruction, it is used for the serial input data also. It is used to see that read the status that which of the interrupts are pending and which of them are masked. And also it is used to see that the interrupts are enabled or not enabled. Okay. So this was the RIM instruction. So we studied the masking of the interrupts, how they are masked using the RIM and the SIM instruction. So the next topic is the timing of interrupts. So when the interrupts are given to the microprocessor, for how much time the interrupt should be provided, or the minimum and the maximum time period of the interrupts, it has to be decided by the programmer. So the longest instruction available in the microprocessor So the interrupts, when they are given to the microprocessor, these interrupts are sensed by the processor one clock cycle before the end of execution of each instruction. So whenever an instruction is written in the microprocessor memory, that instruction is first decoded, then it is means it is first fetched, and then it is decoded, and then it is executed by the microprocessor. And the execution of each instruction, it is according to the t states or according to the clock cycles. So the interrupts, they are sensed by the processor one clock cycle before the end of execution. Suppose that any instruction is executed by the microprocessor and it requires 3 clock cycles. So when the instruction is being executed by the microprocessor, and suppose an interrupt is given to the microprocessor, so the microprocessor will sense that interrupt one clock cycle, that is at the end of second clock cycle. In the second clock cycle, that interrupt will be sensed by the processor. So the minimum time or the minimum timing of the interrupts, it is decided by this, that at that time that interrupt will be should be available so that the microprocessor can sense that interrupt. So the longest instruction which is there in the microprocessor instruction set, it takes 18 clock periods. So we can say that the interrupt signal, it should be available up till 17.5 clock periods so that the microprocessor can sense that interrupt. So the longest instruction, because it is taking 18 clock periods, so when the microprocessor will execute this instruction and suppose an interrupt is given, so that interrupt should be available at least 70 till 17 clock periods so that the microprocessor can sense it, because one clock cycle before the end of execution, interrupts are sensed. Okay, so this 17.5 clock periods, it gives us the minimum pulse width of the interrupts. So this is the minimum pulse width of any interrupt, that it should have 17.5 clock periods till it should be available. Now what will decide the maximum pulse width? Maximum pulse width, suppose at there are 4-5 instructions written in the microprocessor memory, and at the second instruction the interrupt is being given to the microprocessor. Okay, at the second instruction. So when this instruction is being executed, suppose it takes 3 clock cycles, so the interrupt will be sensed at the second clock cycle. Now the interrupt length is so long that after it is being sensed, like at the second clock cycle, it will be sensed by the microprocessor. Then microprocessor will jump at the interrupt service routine, wherever at the address where the interrupt service routine is being written, and then execute that service routine, then return to the third instruction. But when this third instruction is being executed, at that time also this interrupt signal is available. So again the microprocessor is going to sense this interrupt, and again it is going to jump at that address and going to execute the interrupt service routine. So again and again, if the length of the interrupt signal is very long, then again and again it is going to be sensed by the microprocessor, and again microprocessor is going to jump at the service routine address, it is going to execute that, and again it is going to return to this. So the same process is going to repeat again and again. The interrupt is going to be acknowledged by the microprocessor. So the maximum pulse width, it is decided by the condition that the interrupt signal should not be acknowledged again and again by the microprocessor. Its length should be such that only once it is acknowledged, then second time it is not acknowledged by the microprocessor. So maximum pulse width it is decided by the condition that the interrupt signal must not be recognized once again, and it is decided by the programmer. Okay. So in this timing of interrupts, we studied that what should be the minimum pulse width, that is 17.5 clock periods, and what is the maximum pulse width of the interrupt signals. So in this video, we studied about the interrupts which are available in the 8085 microprocessor. Then we studied that how they can be masked, and unmasking of the interrupts can be done, and what is the priority of the interrupts, what are the types of interrupts available in the 8085. So we studied about the 8085 interrupts. So I hope that this video is clear to you. Thank you.